All right. Let's cross our fingers and make sure this thing is working. I see some green up there, so it's supposed to be recording the system and hopefully recording my voice. We'll figure it out there. But I'm banging on it and it's not going real well, but it's at least doing something or other. So, all right. So we're going to see if this video system works here. I think they put a whole new computer in. Cross our fingers. All right. Couple of things. Number one, you got an email from me this weekend, and for that, I am sorry. The math department is maneuvering around because we had a problem with the WebWork server. So WebWork 1 was already closed. That was fine. Your WebWork homework set number 2 was open. And of course, when you move it to a different server, it doesn't save your grade. So if you like the grade that you got, don't click on the WebWork homework number 2, because once you click on a WebWork, it's got to link back to the system. And if you don't do anything, you're going to end up being a 0 because it's back to no answers and stuff because it's a completely different server. So if you want to keep your grade, you got that 95 or 100 or whatever, don't click on what homework number 2 because it'll refer back. So, but the bad news is, if you want to do homework number 2, if you like got 21 or 40 or 2 or whatever, because I saw several different grades on that one, you're going to have to redo any problems that you did before. You're going to have to redo them again. And of course, the numbers will change because it's WebWork, but you're going to have to But the good news again is I extended it. It was like due today or something or other. I actually pushed it back a couple more days for you guys. So get it done. So there you go. All right. So the next thing is this. We're working on the cross product. So we have already done the dot product, and when you take a dot product of 2 vectors, you get a scalar. And as long as the vectors are the same size, you can actually do a dot product of any of them. It's just the X component multiplied together, added to the Y component, multiplied together, added to the Z component, multiplied together. And if you got a 4-dimensional one, added to the T component, multiplied and added together. And so, it's classic dot product, but you can do that on any size vector. Cross products are special. They only work in 3D. You got to have an R3, a 3-dimensional vector and stuff like that. Somebody left their iPad in class and they're looking for it. Oh, well, turn that thing off for me. There you go. All right. For that, it's going to cost them. All right. So with that, cross products have got to be push a button until it works. That's what I do. All right. So cross products have got to be there you go. Cross products have got to be 3-dimensional. And what's special about a cross product is that when you cross the 2 vectors, you get a perpendicular or orthogonal vector to the original 2 guys. So with that being said, let me switch over here to the dot cam. Here we go. And so here we go. With this is what we did last time. You have to do basically the determinant. Remember, it's got to be an R3, so it's going to be a 3-dimensional vector. And what you do is you put your vectors in the column here. And just to remind you, it's called expansion by minors, is how you take a determinant. We did this problem last time of a 3 by 3. You start with the top row. This is positive, negative, positive, positive A, and then you do expansion by minors of blocking off the row of the column with that A in it. And there's your minor matrix down there. And there'll be minus B because they alternate signs, knock off the row and column with a B in it. And then you got the minor matrix below that. And then it'll be plus C. And then you knock off the row and column with C in it. And there's your sub matrix down here, the minor matrix. And it's 2 by 2. So to take a determinant of a 2 by 2, you do main diagonal minus off diagonal, and it gives you a numerical answer. So we did this problem last time to remind you guys. Now, when it comes to doing a cross product of these guys, I think the thing seems to be working. Cross our fingers. Yeah, the big thing is the audio working. Did you come check, make sure the audio is working on this thing? Sure. All right. So while I'm doing this, and hopefully the audio is working, otherwise this would be a complete waste. Just check the audio very quick. Sure.
Go ahead and talk.
Keep talking.
Hello. Yeah.
Okay. A little bit of green. All right.
Yeah. We put in a computer in here.
Yeah, I thought you did. I appreciate it. All right. What I've learned also about this university is squeaky wheel gets the oil. You complain loud enough, something will happen. All right. So with that, and I am sorry for showing my rear end last time in front of you guys, but I was righteously angry. So, say the least on that. So finally we got the system working again, and I'm going to go back and do something or other, probably make more videos on my spare time, like I have any, and see if I can get you guys called back up. Cause I know people keep asking me, well, can't you just post your notes? You guys don't have that kind of cash to make me post my notes. So I'm going to try to do these videos. And if it doesn't work on the videos, then I'll go plan B. I'll post notes, but I'm going to try the videos first, because making you guys watch this mess reinforces your brain. Me just throwing notes out there, I've done that before. Homework solutions, things like that. My grades just died because, that looked good. Answer's 3. They actually didn't study the problem. When you watch a video, you got to study the problem when I'm doing it. So speaking of problems, let's take a look at this guy here. And I kind of set you up here with this. All right. So when you want to take two vectors, and this is very general, but this is how you do a cross product of two vectors, picking up where we left off last time. U is going to be U1, U2, U3, and V is going to be the vector V1, V2, V3. Notice the pointy brackets, those are vectors, all right? And how you do it is you're going to make a 3x3 matrix, and we're going to go old school on this IJK. You put the IJK across the top, and you put, now this is order matters, order matters. The first vector that you're crossing, U cross V. U goes in the second row, V goes in the third row. Because if I did V cross U, you would have to switch it, and it literally will change your sign. So it makes a difference. U cross V. U is in the second row, V is in the third row. Now, you're going to do expansion by minors. So remember your sign deal here. This is plus, minus, plus. So you're going to take the I, and you're going to knock off the row and column with the I in it, and you get the U2, U3, rest of it, V2, V3. But then it's going to change signs. It'll be a minus J, and you knock off the row and column with J in it, and you see your sub matrix down there, U1, U3, U1, U3, V1, V3, and then back to plus, back to change your signs, back to plus K, knock off the row and column K in it, and then you end up getting U1, U2, that is up there, V1, V2. And now, if you want to extend this out to get your actual vector, this would be equal to I times main diagonal, that would be U2 times V3, minus off diagonal, U3 times V2. And it'll be a minus J times main diagonal, U1 times V3 minus off diagonal, U3 times V1, and then plus K, main diagonal, U1 times V2 minus off diagonal, U2 times V1. And these will be numerical values, but it's I, and don't get a minus J, so the negative is going to put in here. Get your J component and then your K component, and there's your three-dimensional vector. And to remind you, this is a three-dimensional vector. So if you had, this was vector U, this was vector V, sticking out at the same point, you've got this third vector over here. This would be U cross V, where the U cross V is perpendicular to the original two vectors. Orthogonal, could be fancy with the words there. Does that make sense? Yeah. All right, right-hand rule is you went U cross V, and it's your thumb. So you have to envision taking U, crossing it with V. So go into your palm, cross it with V, and the sorry about that. The thumb is the perpendicular vector to both that. And so if I do U cross V, it goes up, and that's what I'm trying to draw up. But if I did V cross U, and only way if I'm going to go V cross U, and you got to turn into your palm, you got to go this way, you'll get the same vector, except you can't see it there, but your thumb is actually going to be going downward. So it'll be negative that. Does that make sense? So here's our great example. Let's do something with some real numbers here. Now, this concept is incredibly important, and I will hopefully we'll get to at least a little bit of that today to show you. All right, here we go. Let's let vector u be the vector 1, 3, 4. Let's let vector v be the vector 2, 7, -5. What would u cross v be? All right, so if I want to do u cross v, you make yourself a big 3x3 matrix, and the top row will be the I, J, K. It's u, so the u goes in the second row, which will be 1, 3, 4, and v would go in the third row, 2, 7, -5. So here we go. This would be equal to, you take I, and then we're going to knock off the row and column with I in it, and you're going to get your 2x2 matrix, which will be numbers 3, 4, 7, -5. Okay, again, you knock off the row and column with I in it, and there's your minor matrix. But then it alternates signs, plus, minus, plus, so this will be a minus J. Knock off the row and column with J in it, and I got a 1, 4, 2, -5. Got that in there, 1, 4, 2, -5. And then I got a plus K, knock off the row and column with K in it, and I got 1, 3, 2, 7. 1, 3, 2, 7. Now it becomes number crunching on a 2x2 matrix. Remember, main diagonal minus off diagonal. So continuing on, this would be 3 times -5. So I times 3 times -5 minus 4 times 7. Minus J, and it would be 1 times -5 minus 4 times 2. Plus K times 7 times 1, 1 times 7 if you will, minus 3 times 2. Okay. And then close that sucker off there. And now let's crunch some numbers. So this would be I times -15 minus 28 minus J times -5 minus 8 plus K times 7 minus, that's 3 times 2, which is 6. And remember, I made up these numbers, so no guarantees on any decent numbers on this thing. So what do I got here? A minus 15 minus 28 is a negative 43I. And it's a minus J times, this is for your benefit, minus 5 minus 8 makes it a minus 13. Plus K times 7 minus 6 is 1. I can do that kind of math. But then clean up this guy right here. What's a minus J times a minus 13? Plus 13. So you end up getting negative 43I plus 13J plus 1K. And because the original vectors were in the famous pointing bracket notation, it's proper etiquette to rewrite it back in proper pointing bracket notation. Negative 43, comma 13, comma 1 would be my U cross V vector, which is orthogonal or perpendicular to these original two vectors. Does that make sense? It's not hard, tedious, absolutely, no arguments there, but I hate to tell you, you're now in Calc 3. It's only going to get worse on the tediousness with the kind of material you're going to be working with, but it's not overly difficult. But as I mentioned that, where most students will screw this up, especially when I teach linear algebra, and we do somewhat the same thing with that when we deal with vectors in linear algebra, bonehead careless errors. You can see how bonehead careless errors will kill you on this stuff. A negative times a negative ends up being a negative, mess like that. And then all of a sudden you don't have a perpendicular vector, and all of a sudden all your equations are all going to be messed up. So take your time, be careful of the careless errors. So turn back. All right. Some subtle aspects of this stuff that I want to show you. And it is this. We'll blow this one up here. You guys can see the back. What if you take a vector u and cross it with the same vector u? What do you actually end up getting? I want to show you that. So let's do the math. If I take vector u and cross it with vector u, this again would be I, J, K. U would go in the second row, 1, 3, 4. And it would also go in the third row, 1, 3, 4. So when you do your cross product, I mean your expansion by minors concept doing the cross product of this matrix here, you start out with a positive I, positive, negative, positive. Knock off the row and column with I in it, and you get 3, 4, 3, 4. Then it's a minus J times knock off the row and column with J in it, you get a 1, 4, 1, 4. Plus K, knock off the row and column with K in it, and you get a 1, 3, 1, 3. Okay. Now do your 2 by 2 matrices, main diagonal minus off diagonal. 3 times 4 is 12, minus 12. Minus J times 4 times 1 is 4, minus 1 times 4 is 4. Plus K times 1 times 3 is 3, minus 3 times 1 is 3. And you pretty much get 0I plus a negative makes it plus 0J plus 0K. Or you get the 0, 0, 0, which is known as the zero vector. It's not a zero number, it's a zero vector. Okay, so I want you to look at this is when I do that right-hand rule, that U cross V, that right-hand rule, and the more I cross, the longer the vector goes. So just to kind of describe what's going on here, if I did this, U cross V. Now I'm trying to show this from visual perspective, so hang with me here. U cross V. U and V have a very small angle between the two. Notice my awesome picture. If I did U cross V using the right-hand rule, you're going to get just a little short perpendicular vector because you don't have to do much crossing and you get the little bitty thumb here. But if I did something like this, U V is over here, and I did U cross V. This is a much larger angle. And with that larger angle, you're going to get a much taller vector out of it, okay, of your U cross V. So that angle is going to pay attention in terms of what's the magnitude of that cross product vector going to be. The more you have to kind of run across, cross it with the thumb, the longer the vector is going to be versus, two vectors have a small angle between the two of them. It's going to be a short vector. Still, it's going to be perpendicular. But in this example, when I did U cross U, here's U, cross it with itself, you end up getting, it's got no magnitude at all. I mean, it's a perpendicular vector, but it's zero. So it's basically a dot. Does that make sense? Because you don't have any angle at all, but it's still a vector on this guy. All right. Another aspect of this is a major theorem here. And that is this. If U vector and 3 vector are two 3D vectors, and remember, I put that little notation before, R3, that means that the components are coming from the reals, but it's 3-dimensional. Now, this cross product stuff is very particular. It only works and only defined over 3 dimensions. Okay. So if U and V are 2 vectors of R3, 3D vectors, and theta is the angle between the 2 vectors, then you saw something similar to this. But this one is the magnitude of U cross V is equal to the magnitude of U times the magnitude of V times the sine of the angle between the two. This is how you get the angle between the 2 vectors. With the cross product. Again, a little side note here. We had another formula. If you remember, it was U vector dot V vector. And that was equal to the magnitude of U times the magnitude of V, but something extra special. What was it? Cosine of the angle between the two. So the dot product is it gives you a scalar. So this is a number. So you can actually go take the cosine inverse of this guy when you go run the math here. This gives you a scalar. This one gives you a vector. So we had to put the norm, or the absolute value, if you will, the magnitude of the vector, so you can get it back to a number. So this is a number of the cross product. This is a number of the U vector. And magnitude, this is the magnitude of the V vector. So these are magnitude, so these are numbers times the sine of the angle. So there's a nice little connection between the two here. And then as we just proved up here at the top, a corollary to this guy is this. If U and V are two-dimensional vectors such that U and V, look at the word that I used. I didn't say it was the same, but you can imply this, are parallel, then U dot V is going to be equal to the zero vector. What does parallel mean? Well, yeah, I mean, the parallel means they go in the same direction, okay? So they may have different magnitudes. You know, I could have a short vector going in this direction. Okay, I see if I can draw this for you guys. I can have a short vector going in this direction. I can have a longer vector going in the same direction, okay? But when I try to do the cross, the initial point has to be at the same spot. So when I put them together, there's the short vector, here's the long vector. So when I do U cross V, the angle between the two of them is zero, making basically the magnitude of this guy, sine of zero is zero, make the magnitude zero, and the magnitude zero vector is going to be the famous zero vector itself. So there's your proof. Does that make sense? So they don't have to be the same vector, but parallel. So there's a little extension on that. Okay. Application stuff here. Now, you got a web work problem on this stuff, very similar to this, and they try to mess you up. So I'm going to try to help you out with not getting you messed up on this. We have a theorem. It says this. If you want to know the relationship of this stuff geometrically, here's a great little theorem for you. If U and V are two 3D vectors, again, coming from that famous R3 coefficients from the reals there, components from the reals, then the length of U cross V, denoted magnitude of U cross V, is the area of the parallelogram created from, get my words right here, because I just go from the vector U and vector V. So here we go. If this is vector U, right here, and out of the same point, I got vector V. If I did U cross V, the magnitude of the vector U cross V, which is perpendicular to both of them, would actually be equal to the area of the parallelogram that was created. Does that make sense? Did I lose you guys anywhere? Okay. And so U cross V and V cross U would be the same thing magnitude wise. We're talking about a distance. It's going to be positive. But here's the question that you're going to have. So note right here, this is something special for you guys. Make sure you get it down. Note, web work is going to ask you, what is the area of the triangle created with vector U and vector V? Okay, so what would that be? So here again is vector U, here is vector V. And what they're talking about here is if you cut this thing off and make it a triangle, how would you get the area of that triangle? What would it be equal to? Exactly. You got the parallelogram here, and it made up of two triangles. Think about it. If you just kind of slice it right down the middle there. So you got it. So this would be actually equal to the magnitude of the cross product divided by 2, because you're just splitting it right down the middle. This was with the theorem in the book, of course. This was the question on web work. You're supposed to make that connection that if I talk about the triangle, it was half the parallelogram. So multiply your cross product, magnitude of the cross product by 1/2. Does that make sense? Again, what you're seeing here in Calc 3 is a bunch of formulas, but they all have applications. But you're going to really see some of that interesting stuff when I get you in the section 10.5. All right, so here we go. I got to give you an example here, but here is how they're going to do it usually. We don't just give you vectors. That's too easy. Here's a vector, here's a vector. Okay, great. Take the cross product. Well, okay, maybe the first one will do that one to you because it's nice. This one right here. Here's the example. It says this: find the vector perpendicular to the vectors and the plane containing the points 1, 4, 6, -2, 5, -1, and 1, -1, 1. Find the vector perpendicular to the plane. This is a visual thing. And that's the key to Calc 3, is it being visual. So let's draw this thing out. All right, so somewhere out here in space, don't really care, we got 3 points. We got the point P right here, which is 1, 4, 6. This is not drawn in any kind of particular order here, just hang with it. So here's vector a point Q, which is the point -2, 5, -1. Here's another point over here, point R, which is 1, -1, 1. We're going to throw some words at you guys. Here's one right here. Coplanar. Sounds impressive. What does it mean? Well, first off, you know what a plane is? Sheet of paper. Think about it. Okay. So what a plane is, it's just a flat, two-dimensional in your three-dimensional concept here. It's a sheet of paper in 3D. That's what a plane is. Coplanar means all these points lie on a particular plane. A plane will contain all 3 of these points. So I'm going to try to draw that out for you guys. So here's my plane right here. Okay, here's the plane, 3D, whatever. So there's my plane right there. All 3 of these points, it takes, let's go back old school. How many points you got to have a line? 2. We're adding on a dimension. So how many points you got to have a plane? 3. 2 makes a line, but with a line, how many planes go through a line? An infinite number. You can have it going up, vertical, horizontal, at an angle, at another angle, at every different angle you can think about. If you think about a line, how many planes go through a line? Well, you can have, I don't know if I can draw this to do you guys any justice. You can have an infinite amount of planes that go through a line. Does that make sense? You got them going this way, okay? You got them going this way, okay? There are an infinite number of points going through a line. That's 2 points. But once you throw on that 3rd point, only 1. It's coplanar. There's going to be 1 plane that contains all 3 of these points. Does that make sense? And what we want here is a vector that is perpendicular to this guy. Now, what I need to get you guys trained on is this. When you hear the words perpendicular or orthogonal, the first thing that should come into your brain is cross product. You're being programmed. Just like in Calc 1, when you got the slope of the tangent line, you should be thinking derivative. Area under the curve, you should be thinking antiderivative. All right, when you hear the word perpendicular orthogonal in the world of vectors, you should be thinking of cross product. So to create this guy, you need to have a couple of vectors. I got points. I don't have vectors. So I'm going to create vectors, and this is something you need to master. When they give you points, you're going to need vectors. So, and when you do this cross product stuff, you always want the terminal point to be the same. So watch what I'm doing here. I'm going to find the vector PQ from P to Q. Here it is right here. I'm just going to kind of dot him out there. Now, how do I find that particular vector? Well, this is day 1 in this class. To go from points to a vector, you do end minus beginning, component wise. So again, in your brain, end minus beginning. Okay, so that would be -2 minus 1, comma, 5 minus 4, comma, -1 minus 6. Okay. So here's your first vector, -3, 1, minus 6 is a -7. There's one vector right there, -3, 1, -7. Now, from that same terminal point, I'm gonna create another vector. Okay, so I'm gonna create the vector PR, starting at P, going to R. N minus beginning, 1 minus 1. Minus 1, already doing my math in my head there. 1 minus 1, comma, negative 1 minus 4, comma, 1 minus 6. N minus beginning. Does that make sense? It creates me another vector. This would be 1 minus 1 is 0, negative 1 minus 4 is negative 5, 1 minus 6 is negative 5. So the vector P to R, PR, is the vector 0, negative 5, negative 5. Does that make sense? Now that you've created these vectors, now you can get that perpendicular vector, and it's going to be perpendicular to both vectors, though these vectors are inside this plane. Perpendicular, that means it's going to be perpendicular to the plane. So I'm going to figure out what P Q cross P R is going to be. Now notice there's a third vector I could have created over here, but I want to have that initial point to the other two guys. So you really do get that cross product. You want to have that initial point, one vector going one way, same initial point going the other. So when you take the cross product, that's going to give you your perpendicular vector. Yeah. No, now because there's two vectors that are going to be perpendicular, one going up and one going down. And the only difference is whether you're going to do PQ cross PR or PR cross PQ. It's going to be the same numbers, except all the signs are going to be different. They'll be negative that. So, and we're good with that. Does that make sense? Yeah. And believe it or not, it'll change the magnitude, but it won't change the direction. And the direction is what we want to be perpendicular. You got it. So let's find what that guy's going to be. So this is going to be the famous, here we go, IJK, -3, 1, -7, and 0, -5, -5. And again, the most important concept is I use that same initial terminal point. I started with P and I moved out. Okay. So here we go. I times knock off the wrong column with this guy in it. And I get 1, -7, -5, -5. Minus J times -3, 0, -7, -5. I'm sorry, back to cough drops again. Plus K. -3, 1, 0, -5. Okay. See here. So now let's do the 2 by 2 cross products. Told you I went to the store today to get these things. All right. All right. So here we go. I times 1 times -5 is -5, minus -7 times -5 is 35. Minus J times -3 times -5 is 15. Minus 0 times -7 is 0. Plus K times -3 times -5 is 15. Minus 0 times 1 is 0. So I get negative, what's that? 40I minus 15J plus 15K. Or I could write it as -40, comma, -15, comma, 15. Does that make sense? On web work, because they want that unique answer, because, you know, I could have done PR cross PQ. Is everything okay? Okay, I could have done PR cross PQ, and then I would have gotten the vector 40, 15, -15, right? But then maybe I just want to be different because, you know, Dr. Taylor loves to use that P point. I wanted to use that Q point, and I did the vector P to Q, and then from R to Q or something like that. And I wanted to do something different because I'm just weird. So fine, you can do it that way. You'll still get the right answer, but the only difference is going to be the magnitude of these guys. The numbers will be slightly different, but it'll be in the same direction. So how can we create a unique vector that just points as perpendicular? Very important. So to get this unique vector, you can make him a unit vector. You remember the definition of a unit vector? A unit vector just points. It has a magnitude of 1. So to find a unit vector, it is the vector divided by its magnitude. Does that make sense? So if this is my cross product, of course, I'm running out of room on this guy, but no worries there. I got more paper. How do I make this into a unit vector? So here's the vector PQ cross PR equals the vector -40, -15, 15. And then the unit vector would be the vector -40, -15, 15, divided by the magnitude of the vector, right? So this is your PQ cross PR divided by the magnitude of PQ cross PR. How do you take the magnitude? You take the square root of each component squared. -40 squared plus -15 squared plus 15 squared. Oh, time for a calculator now. These will be big numbers. That's okay. -40 squared. Notice wonderful use of parentheses on this guy. Let me put it in the light source. You guys can see a little bit better. There you go. Plus parentheses -15 squared. -15, John. Wrong button there. -15 squared plus 15 squared. That's 2050. So this would be the vector -40, -15, 15 divided by the square root of 2050. And the square root of 2050 is some crappy number, 45.27, whatever. I made up these numbers anyway, so I wasn't anticipating anything being nice. So here it is. So how would I write out the unit vector of this cross product? Because they're going to want you to put it in component form, pointing bracket. This would be -40 over the square root of 2050. -15 over the square root of 2050. And 15 over the square root of 2050. Does that make sense? Did I lose you guys anywhere? This would be pointing it this way. And watch web work. They're going to do this. Because they want everybody to get the same answer. One, they're going to tell you to make it a unit vector, and then they're going to do this. Also, make the X component positive. Because remember, it could have gone up or it could have gone down. Unit vector is just one length down. I'm just one direction. But when you make the X component positive, everybody's answers are going to be the same. Whether you did, you used the Q point as your base point or the P point or the R point, you're all going to get the same answer. So to actually get the answer on this thing, so watch this on web work, you'll end up getting notice mine's negative. It will now be 40 over the square root of 2050. To make that positive, you multiply everything by -1. And so that'll be 15 over the square root of 2050 and -15 over the square root of 2050. That would be the acceptable answer on web work, and it will give you credit. Well, geez, Dr. Taylor, what I know about some square roots, couldn't you rationalize that denominator a little bit? Yeah, I could. And again, you guys don't pay me enough. And number two, web work doesn't care. As long as it's going to crunch the numbers, it's going to go decimals on this thing anyway. So we don't care about rationalized denominator or, I can factor out 100 or something out of this thing or whatever, and square root of 100 is 10. And I could do all kinds of, make it look good, but it's not gonna matter. Might as well just leave it the way it is. Does that make sense? Yeah.
Pick any starting point and do two vectors with the same terminal point. You'll get this if you're making it a unit vector.
Yep. Let me show you. Okay. See my picture? It was an awesome picture. Let me redraw it for you. All right. So what you're telling me is this. Here are my 3 points. P, R, Q, whatever. I did this. Huh? And to make it a unit vector, I scaled it down, but that became my vector. If I did this, R to P, and R to Q, and I did the cross product, I would get this guy. Now, it may be a different length vector. It's still gonna be perpendicular, but once you make it a unit vector, length one, it's gonna be the same. All you did was move the vector to the back. Or you could have done this. And did the PQ and RQ, make this a vector. And when you make it a unit vector, because it's a directional thing now, they're all going in the same direction. And when you make the X component positive, instead of, fish, I could have gone, down this way. But when you make that first component positive, everybody, all of them are gonna be the same. All right, so let me get back over here to my papers here. Now, there's a big old part B to this problem. I just said it was continued there. What is the area of the parallelogram of this thing? Notice I use these same points. So when I did the same points, here they are. Okay. And this time I'm going to put the P right here. This was your P, 1, 4, 6. This was your Q, -2, 5, -1. And parallelogram, this would be the other point right here, R, which would be the point 1, -1, 1. Right? We have a formula. And the formula is that the area of the parallelogram would be equal to the magnitude of the cross product of the two vectors. Now, what two vectors did I create? I created the vector P to Q. Okay, cross with that other vector, which was P to R, right? So what we need here is, see last problem. Wait a minute, got it right here. What did I get when I did PQ cross PR? What did I get? -40, -15, 15. I got the vector -40, -15, -15. Positive 15, sorry about that. -15, positive 15. Does that make sense? So to get the area of the parallelogram, I had to create the two vectors, which I did in the last problem. So I got that perpendicular vector. Now all I got to do is take the magnitude, the norm, you call that, of the cross product perpendicular vector. So what would that be? I think I've already done that, but let's do it again. This would be the square root of -40 squared plus -15 squared plus 15 squared. And I believe I got the square root of 20, 50. Does that make sense? But WebWorks going to throw this one at you guys. Oh, sorry. What's the area of the triangle created by these 3 points? You got it. So just a little side note right here. Area of triangle created by point P, point Q, and point R points would be equal to the square root of 2050 divided by 2. Does that make sense? So again, is geometry. It's not very visual. So I keep telling people, if you don't know, draw it. You can make a plan and a mathematical plan on how to get an answer if you draw the pictures. All right, so back to that right-hand rule thing here. And these ideas of the unit vector cross products, these what we call the basis, as we talked about it before. You got the I component, it goes 1 unit long in the X direction. J component is 1 unit long, positive in the Y direction, and K component is 1 unit long in the positive Z direction. You with me? Now, let's talk about some basic stuff here. What would, and again, this is visual, what would I cross J be? What vector? It's got to be perpendicular to both of them. And since these are unit 1, when you cross them, it's 9 degrees. Cosine 9 degrees will be 1. So what's going to be? Okay. I cross J is actually K component. Right-hand rule. I cross J, you get K sticking out of this guy. Does that make sense? But what would it be if you did J cross I? Catch a pattern. Negative K. Why is that going to be the case? Because when you do J cross I, right-hand rule, the only way you can do that is J cross I. You got to stick your, my arm's in the way, of course. You got to stick your thumb down into the thing and then cross it, going down to go from J over here to I. So it's going to be a negative K. Catch a pattern. What about this one? What would J cross K be? Think about it. J cross, there's the J. Think about your thumb, cross K. What you going to get? You can get the I guy. Hence, what would the K cross J be? Negative I. Going in the other direction when you have to cross them with the right-hand rule. So it's going to be going literally this way to go the K cross J. You're going to get the negative I direction. But now what about this guy? What is K cross I? K going up, cross I going this way. You're going to get J, which means what is I cross K? Negative. You should be able to visualize this from the classic right-hand rule. Thinking about your right hand and which way you're crossing these guys. First vector, cross with the second vector, you get your thumb. And these are your unit vectors of I, X direction, Y, J, Y direction, K, Z direction, A cross J. So I actually put it at the top, which one the positive ones. So I cross J is K. J cross K is I. But I cross, excuse me, K cross I is J. A lot of people do, what's I cross K? Well, that's going to be a negative J. So, but you can figure this out by your classic right-hand rule. Okay. So the last thing on this material is this. Little algebra concept here of the structure of this material. It is this. Theorem. If you got vectors A, B, and C, there are 3D vectors. It's in that wonderful world of R3. 3 components, everybody's a real number. And S is a scalar. Scalar meaning because it's from R3, it's also a real number there, okay? Then, as mentioned to you before, it's just writing it down as a formula, A vector cross vector will be equal to B vector cross A vector with a big old negative in front of it. When you switch them, it changes the sign. So A cross B is equal to negative B cross A, cross products. If you do a scalar times A cross B, well, it doesn't matter where you put the scalar at. You could just put him with the A. You could just hold him out front, do the cross product, A cross B, and then multiply by the scalar. Or if you really want to, because B had crappy fractions in it, you can multiply the scalar times the vector B, and then cross A cross that scalar B. So you can, scalars won't matter, but you can either put it with the first vector or the second vector, or just hold him out front, take your cross product, and then distribute them through. It'll all be the same answer. This is a multiplication concept here. So I've got A cross B plus C. Oh, I do wrong there. Let's see here. I rotated something or other. Let me rotate him back. Keep going. Here it goes. There's buttons up here. Again, who designs this stuff? Let's put the buttons at the bottom where I rest my hand. Brilliant. Okay, that's okay. At least it's working. Come on, look on the bright side, guys. All right, so A cross B plus C. So parentheses around your B plus C. That's the same thing as A cross B, you cross product, plus A cross C. So with this cross product, you can do distribute product. You can distribute a cross product. Does that make sense? But order matters. So if you look here, A plus B cross C, that will be the same thing. You can distribute in the back. A cross C plus B cross C. So this again would be the distributive, but what you do not have is commutativity. A cross B is not equal to B cross A. So you can't just flip up the order. Notice cross C is in the back. It stays cross C in the back after you distribute it because you can't, it's not commutative. So A cross B is not B cross A. So order matters on this stuff. Okay. If I do a dot product of A dot B cross C, that would be the same thing as, it's impressive, A cross B, and then dot that with the scalar C. That is an unusual property of cross products here. And even better than that, if you really want to do a triple cross product, A cross B cross C, okay, that's going to be the same thing as take the dot product of A with C multiplied times the vector B minus A dot B, taking the dot product of A and B and multiplying that times C and then subtracting the two. So there's some interesting properties, and figure out how you got that is basically a wonderful exercise in manipulating the cross product and exactly what you get. But, you know, triple cross products, they're quite painful. So one last thing before I let you go, application. There is something called a parallel pipe. You're getting into 3D. What is a parallel pipe? A parallel pipe is a parallelogram with a third dimension. So I got three vectors, A, B, and C. And so there's B and there's C. Two vectors, B and C makes a parallelogram down here. You see them? And with that A, that third vector, it makes it a three-dimensional thing. So it's kind of like a box, maybe been shifted over a little bit. So it's a box that's kind of falling apart on me or something or other. It is shifted over a little bit. This is called a parallel pipe. Okay. So it's a parallelogram based upon the three vectors. You get a parallelogram here, all the sides are parallelograms. What's the volume of this guy? The volume of this guy is, you got three vectors, and order doesn't matter. You do the cross product of two of them and dot it with the third. Okay, they call it the scalar triple product here. You take two vectors, you take the cross product of those guys, and then dot it with the third vector. The problem is with the dot product, you may get positive numbers or you may get negative numbers. This is a volume. What kind of answer should you get with volume? Positive. So to make him positive, notice I didn't put the norm on this thing. These are absolute values. That's why I wanted to distinguish between the two. Vectors, you take the norm, the length of it is the little double bracket thing. This is absolute value because this is going to be a scalar. It's going to be a number. We want to make sure that number is positive. It may be negative, depending on how you play those numbers with it, but to get the volume of it, it's the absolute value of that guy. Does that make sense? Study hard on this stuff. Next time, we're going to talk about equations of lines, planes, and all that stuff. And all this material we're learning is going to play a part in that particular material. So get good at it, and I'll see you guys next time.
Yes. Right.